In this video, I'm going to finish up on our discussion of alkenes. And I mean, of course, alkene chemistry will come up sort of all throughout organic chemistry and things like that. But this is going to finish up our sort of discussion of just purely looking at the alkene as a functional group and the sort of reactions that we can do with that. All right, so the first one I'm going to talk about is the epoxidation of alkenes, which is, as the name suggests, adding an epoxide onto the carbon-carbon bond over the double bond. So we start with our alkene here. We have this peroxy acid, so it looks kind of like a carboxylic acid, but it has this extra oxygen in here. That extra oxygen will end up in this three-member ring here on our carbon-carbon bond, so that and that's called the epoxide functional group there. And so then we do end up with our carboxylic acid here. And so popular peroxy acids to use are the peroxyacetic acid and the peroxybenzoic acid. There are other ones, and we'll actually run into one here pretty quick, but just to kind of go through the mechanism here. So this is all kind of happening at the same time, so there isn't really one of these things happening first, but what we see is the electrons from this bond right here go to that carbon. The electrons from this double bond from the pi orbital go to this oxygen right here, and it causes these electrons, well, I'm saying causes, but again, this is all sort of happening concerted mechanism here, and so this is all sort of happening right at the exact same time. So we also have these electrons going here and grabbing that hydrogen right there. So you can see over here where I already have the mechanism sort of already filled in. And so we can sort of pay attention to those colors there, because the red arrows are going to show where these red dashed lines here go. And so we end up with this as our transition state. And then so after that goes through, what we end up with is this over here. So we now have the epoxide, where these two red dashed lines here sort of going to the alkene here become full bonds. And then the green ones on here sort of go away. And so we end up with the epoxide and the acid. And so we can see up here sort of where the acid is coming from all the black colored atoms on this one. And so we end up with that as our acid right here and producing our epoxide. And so this is going to maintain the cis and trans geometry for this, because again, this is happening all at once, so there isn't going to be time for this to rotate around a single bond at all. And so we will maintain the cis and trans geometry. So yeah, this is another popular peroxy acid that's used here, this MCPBA, which I'm showing on here, which is just that same one that we had up here, this peroxybenzoic acid, but now we have this chlorine bound to it. So we don't really have to worry about that now. When we get into aromatic rings in a future video, we'll learn a little bit more about what it means to have these other groups attached to our aromatic ring. But anyway, the point here being that if this is a cis double bond, then we end up with a cis bond here with our epoxide group. And if it's a trans double bond, then we end up with the trans groups here on our epoxide. And so when we get to the epoxide, we can also have what is called acid-catalyzed epoxide opening. So the epoxides can be isolated as stable products if the solution is not too acidic. But if it is acidic, then we get this opening of the epoxide. And so this is going to look familiar from other additions that we saw in previous videos. So we have our epoxide here. The oxygen on this is going to go and grab a hydrogen off of here. The electrons go there, and so we end up with a protonated epoxide right here. And then so what happens is we're in water, and so This more substituted carbon here is going to have a higher partial positive on it, and so this water will attack there. These electrons will go onto the oxygen, so we end up with this. Another water can come in, remove a hydrogen, the electrons go onto the oxygen, and so we end up with this propane 1,2 diol here, or otherwise known as propylene glycol. And of course, we could do this on other alkenes as well, but I'm just using this this propylene oxide here, or epoxy propane, as an example here, just because I wanted to have this extra substitution on this one to show that that is going to be the way that that adds onto there. And what we see is that we get anti-additions with this. So this because of, when we end up with this, we have to have this backside attack here onto that carbon. And so what we end up with is if we have something that it can't just rotate around a single bond, we have this trans 1,2 diol here. And so we'll get both enantiomers of it as well. And so we can have the SS chiral centers, or the RR chiral centers here on this, on the addition onto this epoxy cyclopentane right here. All right, so we can also do syn hydroxylation of the alkene. So that's adding the alcohol groups onto the same side. And so one way we can do this is with these metal oxides here. So either with osmium tetroxide or potassium permanganate. And so we will be adding these hydroxide groups here, these hydroxyl groups here, onto the same side of our carbons here. And so the osmium tetroxide, what the book says that I'm using, is going to give us a much higher yield for this, but it's also more expensive, and I believe it's also more toxic than the potassium permanganate. So the potassium permanganate is going to have a lower yield, but it's a cheaper reactant, and it's somewhat less toxic to use. And so the book says that if we want to do something where we need a high yield, for instance, if we're on like the 6th step of a synthesis sort of reaction, so going through a bunch of reactions to try to synthesize something, and so you're already down to a small yield, then using the osmium tetroxide is sort of preferred for that. But if it's if we're doing something where we need to make a lot of something, like on an industrial scale, or if it's like the first step in a synthesis, then using the potassium permanganate is going to suffice for that. And I tried to color code things on here too, so we can see where stuff is actually coming from. So I have on, and I'll just kind of follow the osmium tetroxide, since the mechanism is pretty much the same for both of these. So we have the green oxygens here coming from our osmium tetroxide, then we're adding this water here, which I have in purple, and so that's going to put the oxygens onto the osmium tetroxide here to reform our catalyst, and the hydrogens from it will end up on these hydroxyl groups on here. So if we want to look at this mechanism a little more closely, so we can look here. So what we have is the electrons from this double bond going to this carbon here, then the electrons from this double bond going to this oxygen here, then the electrons from here going to the osmium metal right here. And so we end up with this osmate ether right here. And so then we use this reducing agent, this H2O2, or we can use something that looks like this, as this positive nitrogen bound to a negative oxygen. And so then we form our hydroxyl groups here and reform our osmium tetroxide. So we can look at this mechanism yet even a little bit more closely here. And so we can actually see, and this might be a bit small, but but if you want to see it in more detail, you can go to the link that I have posted here. But we see that we're ending up actually with the osmium here with the OH groups on it. And so that's actually what what this step is doing. This H2O2 here is actually going to reform this into the osmium tetroxide from this osmium here that has the two OH groups on it. But we can see in the mechanism here how the OHs from the water get onto our hydroxyl groups. And so what we have here, so this is bound right here to our carbon-carbon bond, which started as our carbon-carbon double bond. And so we are sort of at the osmate ether step right there. So then we're bringing in a water, that's these atoms right here, this molecule right here. And so the hydrogen is going to get bound to that oxygen, and the water is, or the oxygen from the water is going to bind that to that osmium. So we end up with this right here. Then we just do the same thing to the other side. And so we've detached our product right here with the two hydroxyl groups on it. And then of course from here we will do the H2O2 to end up getting our osmium tetroxide back from that. So again, this is the syn addition. So when we are doing this, say, to a cyclopentene here, we end up with the cis glycol version of it. Or if we do it to like this 3-hexene here, we end up with a meso 3,4-hexane diol right here. And so we're adding that to the same side on there. So we get the cis isomer for that. All right, and so we can also do oxidative cleavage of alkenes. And so in the potassium permanganate hydroxylation, which, like I said, is going to have pretty much the same mechanism as the osmium tetroxide that we were looking at above, if the solution is warm or acidic or too concentrated, then oxidative cleavage of the glycol may occur. So the products are initially ketones and aldehydes, but the aldehydes are oxidized to carboxylic acids under the strong oxidizing conditions of being in the presence of that potassium permanganate. So if the molecule also contains a terminal double bond to CH2 group, that group is oxidized all the way to CO2 and H2O. So we can have the cleavage by the permanganate here. So again, we go through the same step here where we get to our diol right here, our syn diol right there. Then we continue going and we actually cleave it into a ketone. So what we have on our reactant here, we have these two R groups on one side, then we have an R group and a hydrogen right here. And so we end up making a ketone, which is coming from splitting this down right here. The ketone will come from this side of it, where the aldehyde will come from this side of it that has the hydrogen right there. And so then this aldehyde here is going to get oxidized into a carboxylic acid. So this group right here will get changed into this OH group right here. And so, yeah, if that can happen, if the solution is warm or acidic or too concentrated, and so we can get this oxidative cleavage here. We can also cleave these ketone, or these alkenes rather, by using ozone. So that's O3 here. So we have our O3 molecule here. We're going to split down this right here. So when we add the O3, we end up with an intermediate that looks like this. Then we add this sulfide group right here, which will then reduce this down, and we get our ketone and our aldehyde here. And so to look at this mechanism in a little bit more detail, so we have our ozone here, and so this is going to be in a resonance structure. So electron goes there, that goes onto that other oxygen, so it's in a resonance state of, or it's in a resonance form of those two states there. And so our mechanism is going to look like this. So this oxygen here will come and attack this carbon right here. Then the electrons from the double bond will go to this oxygen right here. Then the electrons from this double bond move onto the positively charged oxygen here. And so we end up with this whole thing on here. Then we see that this will undergo another sort of rearrangement here where the electrons from this oxygen here move down to form a double bond right here. The electrons from this right here, and this should actually be at a single bond right here. So that was a mistake. This should actually be at a single bond at this point. So I will remove that because we're going to be breaking that single bond there. So the electrons from that single bond move over to this bond right here to form a double bond, and then the electrons from this single bond here move onto this oxygen. So we end up with an aldehyde here and a ketone here. But now we have the electrons from this negatively charged oxygen move onto this carbon. It's going to push the electrons from this double bond onto this oxygen. And so the electrons from that oxygen will move to this carbon, which will push the electrons from this double bond up onto this positively charged oxygen right here. And so we end up with this intermediate. And so then we will do the reduction with this sulfide group here. And so that will give us our ketone right here and our aldehyde right here, and then our oxidized sulfide right here. So it's adding this double bond to oxygen onto it right there. So this is going to reduce this intermediate right here into our ketone and our aldehyde. And so we can see when we're doing this, so we can break this double bond right here. So we end up with these two aldehyde groups here on this 5-member ring. So this is actually just the same thing as this structure right here. And so we see we get this, from this bicyclic ring here, we end up breaking one of the rings on it and getting just this single cyclic species right here with the two aldehydes on it. What we see is we also have this, so we're going to break this double bond right here, but we also see that this double bond is being oxidized, so we end up with an oxygen on there, and so we're breaking this ring open and ending up with these two aldehyde groups on here. And then this actually comes from this double bond right here, so we're actually losing that carbon right there as this carbon right here. And so it is actually acting like a oxidative breakage of this double bond on here. So on this product, it looks like we're just getting sort of an oxygen put on here, but it's actually because we're losing this carbon group right here onto another oxygen. And so we're forming this formaldehyde right here, and that's going to leave off of there because we are doing this oxidative cleavage. All right, both permanganate and ozonolysis break the carbon-carbon double bond and replace it with a carbonyl group. In the permanganate cleavage, aldehyde products are further oxidized to carboxylic acids. In the ozonolysis reduction procedure, the aldehyde products are generated in the dimethyl sulfide reduction step and not in the presence of ozone, and so they are not oxidized. So with the ozonolysis, we actually keep our aldehyde groups rather than further oxidizing those into carboxylic acids. All right, so we can talk about polymerization using alkenes, and in a way, this is probably actually some of the most important stuff in our everyday life, this polymerization stuff, because so much of everything we have in everyday life are polymers, and so polymerization to make polymers is something that is extremely common just in everyday life. So, pretty much all plastics and things like that are polymers. And so, you can take like whole college courses on just polymer chemistry. So we're only going to really touch on it very tangentially in this video here. But there are three sort of basic methods for polymerizing these things. So there's the cationic, the free radical, and the anionic polymerization methods. And so I will sort of quickly go through each of these. So the cationic one, as the name suggests, is going to be using carbocation intermediates here. So we're going to have the electrons from this double bond take a hydrogen off of here. The electrons will go onto there. And so we end up putting the hydrogen using that Markovnikov method or rule. We're going to put it on the least substituted carbon here. So we end up with this, this methyl group right here and a carbocation right here. So then we can actually go to the next step here. So we bring in another one of these. I colored it green here just so we know which things are which. And these things, I should point out, are called monomers. So these are monomers. So polymers are made up of a bunch of monomers strung together. And so polymerization is just stringing together the monomers here. And so we can have the electrons from this double bond go right here. So we're forming a bond onto that carbocation there, but it's going to form another carbocation right here. So we can bring in another monomer. This one's going to go to that one, but then we're forming yet another carbocation here. And so we can see as we do more and more steps of this, we're going to keep putting these together in this chain reaction that will produce a polymer. So in the carbocation polymerization, boron trifluoride works well as a catalyst. So we want to sort of start this reaction. So here I showed us using this sulfuric acid catalyst, but we can see why this could be a problem, is that then you end up with this sort of negatively charged HSO4, and because this carbocation is so unstable, that HSO4 with a negative charge might actually go and bind itself to the carbocation. And so we want a catalyst that doesn't leave a good nucleophile. And I mean, HSO4 negative is not going to be a good nucleophile, but it's still possible that you could get that bonding to it because, like I said, that carbocation is just so unstable that even something that's a bad nucleophile can possibly bind to it. And so this boron trifluoride is a good catalyst because it leaves no good nucleophile that might attack the carbocation intermediate and end the polymerization. And so with water as a co-catalyst, which binds to the empty p orbital of our boron trifluoride, it releases a proton without leaving behind any good nucleophile. And so we can take our water here, the electrons from it will go to the empty orbital on our boron trifluoride, so we end up with this right here. The electrons from this are going to sort of move onto that oxygen so that we're releasing this hydrogen as this sort of comes from the double bond and takes that hydrogen right there. So we end up with this, and now we've added this hydrogen onto here, and we've produced our carbocation here. But there isn't going to be like a good nucleophile to come and bind that carbocation, or at least the catalyst is not actually going to bond to that carbocation. So we can have our next monomer come in here. We can have this come and bond to it. We add that to it. We can then add another one here that I have in blue, so we can keep adding those. And quite often when you're doing polymer chemistry, you might see something that looks like this, so this circled P here. So this is just telling us that we have sort of a polymer here, and we're just sort of paying attention to the sort of tail end of it where things are adding onto it. And so yeah, then a termination step could be that we have the double bond on one of these monomers come and take one of the hydrogens off of here, go down and produce a double bond right here, so that we end up with our polystyrene here, and then we end up with this monomer right here that has the carbocation, so that can actually be used to start another chain for this. So that, as I said, is the carbocation method of polymerization. The next one we'll look at here is free radical polymerization. And so on this one, we have, well, we're doing a free radical reaction. So we can have one electron from that double bond go here, meet up with that single electron there. Then one of them goes to this carbon right here. So we end up with this radical right here. We're calling it stabilized because this this benzene ring here is going to have that resonance stabilization with our free radical. So we could have this move down to here, that move there, and then this sort of move there, and so on and so forth. I'm not going to go through all of the resonance structures for this. But now we can have this come, we have this go, electron go there, one come from here, and another one go there. So we're adding another monomer onto our chain, so we end up with our growing chain here, and we can keep doing this over and over again until we get a polystyrene that has between 100 and 10,000 of these styrene monomers sort of chained together in this polymer here. So the anionic one is fairly similar to that. So we have something like this hydroxide right here comes, bonds to that carbon there. The electrons go to that one right there. So we end up with this carboanion right here. So this carboanion can then come bond to that carbon there. The electrons move to that one. So we end up with this over here on our growing chain. We keep polymerizing it so that we end up with a long polymer with, you know, some number of monomers bound together on here. So yeah, these are the three basic methods for polymerizing these monomers together. As I said, you could go into a lot more detail on these types of things and get into like the physical properties of these polymers, and then adding, you know, different ratios of different types of monomers together to get different polymers from that have different physical properties. And so, you know, I mean, that's a whole industry unto itself, is plastics and coming up with new kinds of plastics and adhesives and other sorts of polymers like that. And so, yeah, just to point out, you know, this is a very basic overview of this, and you could go into a lot more detail on polymers, polymerization, and the science behind that. But anyway, we will move on to our last topic in this video, which is olefin metathesis. And so in this, what we're doing is, again, we're sort of breaking these alkene double bonds down the middle right here, but now we're sort of switching them around so that we end up with, you know, one of them bound on this side and the other one bound on this side. So we're sort of switching those back and forth. And so this was, you know, a very important discovery. I think the people who came up with this won the Nobel Prize in chemistry. So again, this isn't, you know, just sort of like a gee whiz, isn't that interesting kind of thing. There is actual practical uses for this olefin metathesis. In fact, Schrock and Grubbs, I believe, were two of the three people who got the Nobel Prize for this. And so that's why these catalysts are named after them. So these catalysts that have to be used in order to do this olefin metathesis. And so the Schrock catalysts are these molybdenum catalysts. So these are just three examples of Schrock catalysts. Then the Grubbs catalyst use this ruthenium here as the metal on it, with, you know, these large sort of side chains coming off of it. And so the Grubbs catalyst, these are sort of what they look like in 3 dimensions right here. I got these images from the Wikipedia articles about these things. But anyway, what we're doing is we have our metal right here, and so we see it has this thing double bound to it. If we look up here on these catalysts, the double bound things that they're talking about would be these things like on our Schrock catalysts. It would be these things on our Grubbs catalysts right here. So those are the double bound things that are going to get kind of switched out of here. But what we're doing is we're bringing in one of our reactants right here, and so it's actually going to form this bond here with our metal with that double bond. So if we actually look over at this one, these two cycles here are showing the same thing, but I think they both have their own strengths and weaknesses here. This one on the right shows sort of the arrow pushing mechanism, which I like. And so we can see that the electrons from the double bond on the catalyst here is going to bind to this one right here. The electrons from this double bond right here are going and binding to that ruthenium. So we end up with this sort of square looking thing here. That's what they're showing right here. Then we're going to break off one of the, well, we're going to break off the what's shown on here as the red group here as the electrons move down here, breaking off the ruthenium, and then the electrons from this D right here are going to the ruthenium, and so we're actually releasing off of this, we're releasing this thing off of this. And what I like on this one here on the left is that it's showing that we're releasing this ethene right here, which is quite common in these reactions. And the reason for that is ethene is a gas at room temperature, and so that will actually bubble out of your reaction. So you're removing products from it, which is going to help push that reaction towards the products through Le Chatelier's principle. And so you're actually going to, form a lot. You're going to get a decent yield from it by having this sort of remove this ethene product from it to push the reaction towards the product. So what we're actually removing here is going to be these two carbons right here. And so we end up with this R1 bound to it. Now we bring in our R2. That's actually going to now form a bond with it. So on this side, we can see the arrow pushing mechanism. We're bringing in this right here, which is our R2. So that's coming in. We form this next square species right here. The electrons move. We're going to remove this part from it right here. And so we end up with this right here. Now we're going to bring in this double blue species right here and sort of keep going around in that circle there. So yeah, that is sort of the way that this reaction happens. So we're using these metal catalysts, which has this sort of catalytic cycle, as it says right here, for the olefin metathesis. So you can just keep reforming these different double bonds on here. And so what I show up here too is that we're going to get sort of a mixture of these. So on here I have in blue the A ones right here, and then in red the B ones right here. And so we can actually get these cis and trans isomers for this, and so we could have this H down here or this B up here, and so on and so forth. Some of these catalysts with these big groups are probably going to at least try to control for getting one type over the other. So trying to control for getting the cis over the trans or the trans over the cis on here. And of course, you could just keep reforming the thing that you just sort of broke. So, if we broke this bond right here, we could then just bring in another of the blue A ones and then reform that one again. But anyway, that is sort of why having this ethene leave is really nice because that can help prevent it from, sort of doing the back reaction, and we therefore favor the products in that reaction. So these are just some of the types of olefin metathesis reactions that you can do. So there's what's called cross metathesis. So that's bringing in two of these reactants here. Maybe kind of hard to see, but this one says R and this one's R prime. But of course, you could just bring in R's, the same reactants if you wanted to. And in fact, you're probably going to get some of those made while you're doing this reaction as sort of a side reaction. But regardless, you bring in two of these alkenes here, and then you're just sort of putting them together like this. And we have our ethene here that is leaving, so that's going to leave as a gas and help push this towards the products here. There is also this acyclic diene metathesis, so we have an alkene on either side of this, and so we are bonding just a bunch of these things together. So we'd take, two of these things right here, bond them together, then we end up with something that's even longer that has alkenes on either end of it, and so you can keep adding more and more of those onto it and get a polymer from it. We can also have a ring opening metathesis polymerization. So we're going to break this down here. And so we're going to sort of add two more alkenes onto this, one on this side and one on this side. And so we end up with this with alkenes on either end here, which can then, bond onto something else, probably sort of another form of this right here. And so you can then sort of polymerize this through this ring opening mechanism here. There's also ring opening cross metathesis. So again, we're going to break this down here. We're going to take this and sort of add it onto either side of it. So this shows that we're just breaking it open, and so we end up with this right here. And then this reactant right here is just adding onto this side. We can also do ring closing metathesis. So we're going to sort of take this right here, break that, and bring these together into a ring like this. And then the carbons from the ends of this are going to leave as our ethene group right here. Then we can have a ring opening, ring closing metathesis. So we're breaking this ring and then closing this ring right here so that we end up with something that looks like this. So if you go to this link right here, it actually shows more of these kinds of reactions using alkynes, which are triple bonds. But I haven't talked about alkynes yet, so I neglected to put that part of this chart onto here. But these are the metathesis reactions that you can do with the alkene double bonds. And so yeah, that was everything I wanted to discuss in this video. So again, we talked about the epoxidation of alkenes, so putting this epoxide group on it using this peroxy acid here. So we can make these epoxides. We can then, of course, open these epoxides with acid-catalyzed epoxide opening, and so we get the anti-addition of these two hydroxyl groups, these two alcohol groups. And so if you put it like on a ring like this, then we get the trans isomer for this. We can also do synhydroxylation if we use these metal oxides like osmium tetroxide or potassium permanganate, which puts the alcohol groups, the hydroxyl groups, on the same side here, so that we would end up with these cis glycols or mesohexane diols here. We can also do oxidative cleavage if our solution with the potassium permanganate is warm or acidic or too concentrated. So we can cleave by permanganate. We can also cleave by ozonolysis, which is nice because we don't end up oxidizing our aldehydes into carboxylic acid. So if you wanted to keep those aldehydes, then you would probably want to choose doing ozonolysis rather than the potassium permanganate. We looked at polymerization, so the cationic, free radical, and anionic polymerizations, which polymerization, again, is just adding a bunch of monomers together in a chain through these chain reactions to form a polymer, which are used in a lot of things like plastics and adhesives and stuff. In fact, some of these things like the polystyrene, you might actually recognize that name. Uh, so down here, I didn't put the name on here, but I believe this is actually the polymer for super glue. So I think this is actually the super glue polymer right here. But then the last thing we talked about was the olefin metathesis, which is just breaking these double bonds, these alkene double bonds, and then reforming alkene double bonds where we can sort of switch these things around here. And so we can do that with these Schrock catalysts or Grubb catalysts in this catalytic cycle. But anyway, I don't want to drone on too long. The next video is going to be about alkynes. That might end up being 2 videos, but there probably won't be as many of them as there are with these alkene videos, especially since a lot of the reactions for alkynes are very similar to the alkene videos. But anyway, I hope you found this video helpful, and I will see you in the next one.